So let's talk about mapping the components. Now, no pressure, but this is the single most important step in the whole process. Even more, this step determines how the system will look like in the long run, and to top it all, once set, it's not easy to change. So in other words, mapping the components of the microservices architecture should be taken very seriously, and it's not something that can be done offhand. This step will literally shape the system, and a lot of thinking should be invested in it. So what exactly is mapping the service? What should we do in this step? Well, the definition is actually quite simple. In this step, we are defining the various components of the system. In other words, we map the various parts of the system that, when working together, compose the whole system. So, for example, we might define a component that handles orders, another one that handles payments, and so on. Now, it's important to remember, when talking about components in microservices architecture, we actually talk about services as opposed to libraries in a monolith system. This is an important distinction because services behave differently than libraries and have their set of constraints. For example, since service is an out-of-process component, every access to it requires network traffic, which is a problem from a performance point of view. So we wouldn't want to design a service that the client accesses too frequently. And this is just one example. So anyway, keep in mind we are talking about services here. So how do we do that? How do we decide what are our components? Well, when mapping the components, we should base it on several factors. These factors are business requirements, functional autonomy, data entities, and data autonomy. So let's see what these factors actually mean. And let's begin with business requirements. So when talking about business requirements, we talk about the collection of requirements around a specific business capability. We need to identify the various business capabilities of the system and understand what are the requirements for each one. For example, a business capability can be orders management, meaning the system should manage orders received by customers. This is a business capability, and there are requirements that support it, such as add new order, remove order, update order, calculate the amount of orders, and so on. Each one of these requirements relate to the orders management capability. So when mapping the components of the system, we usually use the business capability as a frame for the component, and the requirements are the actions the component can do. So in this example, we will have a service that handles orders and that exposes methods for adding, removing, updating, and calculating orders. So this is one factor of mapping the components. The next one is functional autonomy. What this means is this. Functional autonomy is the maximum functionality that does not involve other business requirements. So if our business capability is, say, telemetry processing, the service should handle everything related to the telemetry processing, but should not handle functionality that involve other capabilities. For example, exporting the telemetry to other systems. This should be done by other services. So let's see another example. Remember our order management services from the previous slide? So this service might include functionality to retrieve the orders made in the last week. This functionality fits quite well inside the business capability, which is orders management, and therefore should be included in the service. However, a functionality of getting all the orders made by users aged 34 to 45 might pose a problem. This functionality involves data not related to orders, so on the surface should not be included in the service. However, when mapping components, you will almost always stumble upon some gray areas. It's really difficult, not to say impossible, to design a system where the services are really fully isolated. Requirements usually do not allow for this, and the real life are stronger than patterns and practices. Therefore, be prepared to have some functionality that rely on duplicate data and inter-service communication, as we discussed in the previous section. The real creativity here lies in having as little as possible such cases. The next factor is data entities. In this factor, the service is designed around well-specified data entities. This is the easiest factor to understand, and to be frank, the one that is used most by architects, and that's fine. Using this factor, we identify the major entities in the system. For example, orders and items, and map our components around them. So in this example, we will end up with a service that handles orders and another one that handles items. As you can see, this is really the easiest factor to work with and definitely the most popular one. Now, it should be noted that the fact that a service is designed around entities does not mean it cannot deal with other entities, but these entities should be related to by their ID, and the service should not store the full entity. One classic example for that is when the orders entities handled by the order service stores the customer ID. Now, the customer itself is not stored in the service's database, and there are no methods in the service to handle customers, but we do need to know which customer made this order, so the database holds the customer's ID. Now, if you would like to retrieve the respective customer, we will go to the customer management service, which is designed around the customer entity, and use the service's retrieval method to retrieve the customer using the customer ID we grabbed from the order entity. This is quite a common pattern, and it definitely does not violate the data entities factor. Our services are still designed around specific entities, but in real life, there is always relationship between entities. Now, the last factor is data autonomy. This factor actually builds on the data entities factor and adds to it the fact that the underlying data is an atomic unit. What this means is that the service does not depend on the data from other services to function properly. If that happens, it's a sign we messed our architecture and we should work on it again and probably include this external data in our service. For example, say we have an employee's service that relies on addresses service to return the employee's data. Every request to the employee's service results in a request to the address's data to retrieve the employee's address. In this example, the employee's service has no life in its own. It always relies on other service, in this case the address's service, to function properly. This is a major sign that our architecture is not optimized. The right thing to do in this case is to include the address's data in the employee's service. True, that will make the service a little bit larger, which is usually something we try to avoid, but the alternative is much worse. We really need our services to be autonomous. This is demonstrated in the organized around business capability attribute of microservices, and it's one of the most important aspects of this architecture. Okay, so we have covered the 4 factors that help us map the various services in our system. Now, let's wrap it up with an example. So in our example, we're talking about an e-commerce system. And in this system, we identified 4 services that follow the factors we just discussed. So the first service is the inventory service. The second one handles orders. Then comes the customer's service. And last is the payment service. And now let's see how these services follow the factors we defined. So first, business requirements. Well, this one is quite simple. As you can see, there is a clear distinction in our services between business requirements. The inventory service manages inventory items. The orders service manages the orders. The customer service manages customers. And the payment service, not surprisingly, performs the payments. So that looks good. Next is the functional autonomy factor. Well, since we already established the services have their own business requirements, it's quite easy to determine that each one of them is autonomous functionality-wise. So the inventory service has a functionality to add, remove, update, and change the quantity of items in the inventory. The orders service can add and cancel orders, and also calculate the total price of an order. The customer's service enables adding, updating, removing, and retrieving customers' details, and the payment service, again, unsurprisingly, performs the payments. So as you can see, the functionality is well defined, and the various methods are autonomous and do not rely on other services. And what about data entities? Well, here also it looks good. The inventory service deals with items in the inventory. The orders service handles the order and the shipping address entities, and note that the shipping address is not part of the customer entity, which makes sense since it's part of the order and not part of the customer. A single customer can use multiple shipping addresses, as you probably know. Next, the customer service handles the customer, address, and contact details entities. Note that this service does not handle the orders history of the customer. This is handled in the orders service. So if a customer wants to view his orders history, he will go to the order service with his customer ID and retrieve the history of his own ID. That bodes well with what we said before, that data in one service can relate to data in other services as long as this relationship is done using the identifier of the entity and not the entity itself. The last service is the payment service, which stores the payment history entities. So again, we have a clear separation between the services when it comes to data entities. The last factor is the data autonomy, and let's see where we stand here. So the inventory has no related data in other services, so we're good here. The data in the order service is related to two other services. The order items are related to the items in the inventory by item ID, and the customer who made the order is part of the customer service and is represented in the order's data by its identifier, the customer ID. So it looks like there is no problem here. The order's data is related to data in other services, but this relation is represented using identifiers, which is not a problem. Next is the customer service, and its data is related to the order's data by order ID. Now note that this relation is not a must, and the opposite direction, where customers are related to orders, might be good enough, but there are cases when we will want it both ways. And what about the payments? Well, the data here is not related to anything. This service only holds data about the payments themselves, and it does not contain data about other services. So all is good. So it looks like our mapping is good and that we can move on with the development. And this is a good example of how a mapping should be done. We should focus on the business requirements, functional autonomy, data entities, and data autonomy, and map our components according to these factors. Note that nowhere in the process did we talk about technology, development platform, or similar. Their time will come, but it's simply too early to consider them, and they won't have an actual impact on the mapping. This step involved mainly business and functional related considerations, and the mapping should be done using these factors only. Now, this is all fun and games, but in reality, systems tend to be more complicated than this, and you will probably stumble upon some edge cases which you will have to consider. So I want to discuss two such cases, both are quite common, and see how do we deal with them. So this is the first case. We need to retrieve all customers from New York City with the total numbers of orders for each customer. This is what we should end up with. So in this table, you can see we have two columns. The first is the customer name, and the second is the number of orders this customer made. Now, this poses a problem because this data is spread across two services. The customer's name is stored in the customer's service, and the number of orders is stored in the orders service. Now, this situation of retrieving data from two or more services is extremely common, and you will definitely have to deal with it someday. So what should we do? Well, to solve this problem, we can use one of three approaches. The first one is data duplication. In this approach, we have the two services, orders and customers, but the number of orders is stored not only in the orders service database, but also in the customer's database. This means that whenever a new order is created or when an order is cancelled, this number should be updated in the customer's service. This might pose a problem when the numbers go out of sync, but the update action itself is quite simple. In this approach, we have data that is duplicated and appears twice, in the orders service and in the customer service. The second approach is service query. In this approach, again, we have the two services, only this time they talk to each other while querying the customers. This means that when the customer's data is retrieved, the customer's service goes to the order service and retrieves the number of orders for each customer. Remember, the order service stores the customer ID that made the order, so this query can be done. Now, the problem with this approach is that it loads the network and the service. If we are going to retrieve 200 customers, we are going to access the order service 200 times, and that's a lot. Of course, we can do it in batches, but then we have a lot more coding to do. The third approach is Aggregation Service. In this approach, in addition to the two services we already have, there is another service that aggregates the results of the queries. What this service does is querying the customer service and then querying the order service with the result of the customer's query. The main advantage of this approach is that data and service are not mixed. The order service deals with orders only, the customer service deals with customers only, and they don't know each other. The results merging is done by additional external service. Okay, so we saw the three approaches. Now, which one should we choose for our specific scenario? Well, my personal recommendation is to go for the first approach, the data duplication. It's not a perfect one and it has its own flaws, but it's better than the other two. The service query has a serious potential for performance problem, and the aggregation service requires additional service and additional development for something quite small. Now, this recommendation is specific for this case, and I like it more because we are dealing here with very little data duplicated, and this data is also read-only, so no synchronization is required. But in other scenarios, the recommendation might be different. But anyway, this is the recommended approach for this scenario, and this is how you should deal with this edge case. And now, let's talk about the second edge case. In this case, we need to retrieve all the orders in the system. Now, on a first look, this looks like a no-brainer. It's a simple query related to a well-defined entity, can definitely be implemented using only the order service. So what is the problem here? Well, the problem lies in the volume of the data retrieved. After a few years, the number of orders in the system will be huge, and retrieving it all in a single request will bring the service and the network to their knees. The load will simply be too big and the service won't stand it. Services are best used for a well-defined amount of data processing, an amount that can be handled quickly and efficiently. But retrieving gigas of data in one request, this is not something a service is designed to do. So what should we do? Well, first, find out what's the purpose of this query. Why would someone want to retrieve the list of all the orders made from the very first day of the system? Usually, such a query is used for reporting. Reports are often used to show trends, and the trends are based on past data. Now, if that's actually the case, you should recommend using a report engine for this query. All report engines out there can work directly with the database, bypassing the service API and performing efficient querying against the database. This way, the customer will have the data he wants whenever he wants it, and the service will not suffer from this query. Okay, great. So these were the two edge cases I wanted to cover. Now, another topic you need to be aware of is cross-cutting services. Now, cross-cutting services are services that provide system-wide utilities, meaning utilities that are not tied to a specific business scenario, but ones that almost every service can benefit from. Some common examples of cross-cutting services are logging, caching, user management, and of course, there are more. Now, the most important thing to know about these services is that they must be part of the mapping. These services can greatly simplify the design and development of other services, and in fact, they usually should be developed early in the project. So make sure to include these in your mapping. Okay, so that concludes the components mapping step in the process, and I hope you now know how to approach this very important task. And now let's move on to the next step.